My name's Henry, and I'm presenting Pilot, Efficient Planning by Imitation Learning and Optimization for Safe Autonomous Driving. This is research done at 5, a UK-based autonomous driving startup. First, I'd like to briefly discuss the 3 foundational pillars of planning for autonomous vehicles. The first is safety. Given passengers will be putting their lives in the metaphorical hands of autonomous vehicles, it's our duty as engineers and scientists to design a system that is as safe as possible. We really take the view that we can't compromise on safety. Not only do unsafe vehicles put their passengers in jeopardy, but they also put widespread adoption of AV technology in jeopardy, as it fosters public mistrust. Runtime efficiency is also important, particularly in fast-moving environments, to ensure the AV can react quickly. This also contributes to the safety of the system when deployed. Lastly, the comfort and smoothness of plans is essential to wider adoption of AVs. We call this planning quality. However, existing methods struggle to achieve all 3 and tend to make a trade-off between these desiderata. The principal trade-off tends to be between runtime efficiency on one side and safety and comfort on the other. Let's discuss 2 popular families of methods that tend to fall on either side of this dichotomy: optimization-based planners and data-driven planners. Optimization-based planners can produce provably safe and high-quality plans, but are typically slow. There's an example of that on the right-hand side. But data-driven planners, however, tend to be fast, but normally have no guarantees of safety or quality. In this paper, we propose an approach that attempts to achieve the best of both worlds by combining these 2 approaches and to satisfy the 3 pillars of AV planning. Our method is an efficient optimizer with a data-driven initialization. This achieves efficiency as the optimization is made easier through an informed initialization, and it guarantees safety and quality as the optimizer provides a layer of protection from the data-driven initialization. So Pilot, the name of our method, stands for Planning by Imitation Learning and Optimization. It uses a deep neural network to warm start an efficient optimizer. The neural network is trained to imitate an expensive-to-run optimization-based planner that is only needed at training time. So let's talk about training. Vanilla behavioral cloning is not sufficient for effective imitation, as errors compound and the distribution over states seen by the expert doesn't match the distribution encountered by the learner. To mitigate this, we use DAGger, dataset aggregation, which augments the dataset online with data from Pilot running in the loop of a simulation. This can be broken down into the following steps. First, pre-training the network using a base dataset of planning problems labeled with plans by the expensive-to-run planner. Then new problems are sampled from the state distribution induced by the learner's policy when run in simulation. The new planning problems are solved by the expert, expensive-to-run planner. These problem-plan pairs are added to the base dataset, which the neural network is retrained on. Then, at inference time, the trained neural network warm starts the efficient optimizer, which, when it converges, ensures the satisfaction of safety and smoothness criteria, without a major reduction in runtime efficiency. We do a case study of Pilot using the 2-stage optimization-based planner from Eiras et al., which is previous work from the 5 Edinburgh team to appear at TRO later this year. And we refer to this 2-stage optimization-based planner as 2S-opt. And we use this here for Pilot as the expensive-to-run expert planner. This planner solves a simplified mixed integer linear programming formulation of the planning problem to enforce hard constraints of safety before feeding the result to a kinematically feasible constrained nonlinear programming solver to produce safe and smooth trajectories. 2S-opt produces high-quality plans, but at the cost of runtime efficiency, making it a good candidate to be the expert for Pilot. In this case study, Pilot and 2S-opt share input representations, and these have 3 components: a bird's eye view of the scene, the reference path the ego attempts to make progress along, and predictions of other dynamic agents transformed into the reference path coordinate frame. If it converges, 2S-opt guarantees a safe and smooth trajectory given those predictions, as feasible solutions from 2S-opt's optimizer can't break hard constraints on safety or smoothness. In our use case of Pilot for 2S-opt, we use the same second stage as 2S-opt. does, the NLP solver, for the efficient optimizer of Pilot. Following the Pilot framework, we use the trained neural network, which has been trained on 2S-opt with L2 loss, to warm start initialize this NLP optimizer. This diagram visualizes the implementation of Pilot for 2S-opt. So as in 2S-opt, the state is first transformed to the reference path-based coordinate system. It's then encoded into multi-channel grayscale images. These were chosen for generalizability and scalability reasons. The spatial encoding allows an arbitrary number of road users in an arbitrary road layout. These images are used as inputs to the CNN neural network layers that has been trained on 2S-opt with Dagger. The output of those is flattened. Other scalar inputs which aren't visualized are then appended and fed into the dense layers. This is then fed to the NLP solver, which is the efficient optimizer, which then outputs a trajectory in the reference path coordinate frame, which is then transformed back into the global coordinate frame. So moving on to the results. Our results cover first how Pilot compares to the expert optimizer imitates. We then have two ablations, one comparing Pilot to the neural network alone, and another compares Pilot to using the efficient optimizer with heuristic initializations in place of the imitation neural network. And lastly, we compare to an external method, constrained policy network. So the results use the Carla simulator. And here we talk about problems, where one problem is a single planning instant, which is one time point with fixed predictions for an 8-second time horizon. And the plans are also for an 8-second time horizon. So we pre-train Pilot first with a dataset of 20,000 problems from Carla's Town 2. We then run Dagger in Town 2 with up to 40 static or autopilot vehicles. And the results that we show here are from comparisons on a benchmarking dataset of 1,000 problems from Carla's Town 1. So here we compare to 2S-opt. Pilot achieves a significant reduction in runtime. It's around 7 times faster when comparing to 2S-opt, which is what it imitates, while hardly sacrificing planning quality. There's a minimal average increase here in the optimizer cost function. And this whole comparison is made over the 962 out of the 1,000 problems from the benchmarking dataset where both Pilot and 2S-opt converge. And this video shows 2S-opt and Pilot actually running with the planner in the loop for this simple overtake scenario. In our first ablation, we compare Pilot to the imitation network alone, that is, without the optimization stage afterwards. This plot shows the constraint satisfaction on the y-axis for Pilot and the network for different hard constraints used by the optimizer. So as you can see, the network, which is in green, doesn't satisfy as many of the optimizer's safety and quality constraints as Pilot does, particularly the equality constraints related to kinematic feasibility. In our second ablation, we compare Pilot to the efficient optimizer when initialized by 4 simple heuristic initializations. This comparison in solve time and cost is only on the problems that both 2S-opt and the efficient optimizers solve. The reduced NLP solve time implies Pilot's neural network initialization produces trajectories that are easier to optimize. One heuristic, constant acceleration, has a slight advantage in NLP cost, but solves far fewer problems and takes significantly longer to converge. And lastly, we are comparing our method to an external optimizer-free method, constrained policy network, or CPN. This trains the neural network directly on a loss function constructed from the constraints optimized by the NLP solver, with ReLUs emulating hard constraints. We used a far simpler training dataset with only 3 static vehicles, as training the CPN was highly unstable. This plot showed that CPN struggled to consistently satisfy kinematic, jerk, or collision constraints. So in summary, we propose Pilot, a method to leverage the best qualities of optimization-based planning and data-driven efficiency, combining low runtimes with guaranteed safety and smooth trajectories, in an attempt to achieve all 3 of the pillars of AV planning. Thank you very much.